In this video, we're going to look at taking the derivative of exponential and logarithmic functions. And to skip out on the proofs of these derivatives, we're going to just go ahead. I'm going to give them the derivative formulas to you, and we're going to jump right in. We're going to apply them mixing in our chain rule. The derivative of the exponential function e to the x is e to the x itself. And if I replace the exponent of x in this next side here with a function of u, which can be written in terms of x, and I take the derivative with respect to x of e to the u power. That would be e to the u itself times the derivative of that exponent, which is du, with respect to x. So that's the chain rule part. And we're going to apply that right here for a couple of examples. So I have this first one. I want to take the derivative with respect to x of e to the 2x minus 1 power. If you want, you can use U-substitution. You don't have to, but you can use U-substitution. Say u is equal to 2x minus 1. And so we basically are trying to find the derivative with respect to x of e to the u power, which is going to be e to the u times the derivative of u with respect to x. And as you do enough of these, you don't have to do the u substitution, but it's a good habit to have initially, because this is the kind of the line that you skip when you're trying to do these without doing u substitution. So du over dx, the derivative of u with respect to x is 2, and then we resubstitute everything in. So e to the u would be e to the 2x minus 1 power times du over dx is 2. And so if we wanted, we could just put the 2 out front. 2 times e to the 2x minus 1 is my derivative. Now let's look at this next one. So I have e to the 3 over x power that I want to take the derivative of. We could let u be 3 over x. And we could rewrite our problem as taking the derivative with respect to x of e to the u, and that's going to be e to the u times the derivative of u with respect to x, which means I need to find the derivative of u. Well, remember, 3 over x is the same thing as 3 times x to the negative 1 power. So du over dx, the derivative of u with respect to x, would equal negative 3 times x to the negative 2nd power, which is the same thing as negative 3 over x squared. And we could plug all of that back in to our line over here. So our derivative of this problem is going to equal e, instead of u I have 3 over x, times du over dx, which we said was negative 3 over x squared. So there's my derivative. Now let's look at this one. Find y prime if y squared is equal to e to the y power, or y squared plus e to the y power is equaling to 2x squared. Well, basically that means find the derivative implicitly. So I start taking the derivative with respect to x of everything. So d over dx of y squared, or in fact I can say dy over dx of y squared plus e to the y power is equal to the derivative with respect to x of 2x squared. Actually, I like it. We're going to say just the derivative with respect to x that way. All right, so what I'd have on the left would be 2y dy over dx plus the derivative of e to the y would be e to the y times dy over dx is equal to 4 times x. Factor out my dy over dx's. And then I would divide by 2y plus e to the y. Now dy over dx is the same thing as y prime. Just two different notations. Now let's look at the natural log of x. The derivative of the natural log of x is equal to 1 divided by x. Now if I had a function of x inside of the logarithm, and apply the chain rule, which is over here on the right-hand side. The derivative with respect to x of ln of u is equal to 1 over the inside times the derivative of the inside. So 1 over u times du over dx. And let's apply that to some examples. Now, before I get to the application, let's actually prove this part. And we can use the implicit derivative to do this for us. So we want to prove that the derivative with respect to x of the natural log of x is equal to 1 over x. The way we would do that is we'll start with y equals the ln of x. Now, we don't know how to do the derivative of ln of x without just using our formula. So what we would do is we would rewrite this in a format where we could take the derivative of. I would write this as an exponential function, which would be e to the y equals x. And then do the derivative of both sides. So the derivative with respect to x of e to the y, the derivative with respect to x of x. Well, the derivative with respect to x of e to the y would be e to the y power times the derivative of y with respect to x. The derivative with respect to x of, is 1. And then we would divide by e to the y. dy over dx is equal to 1 over e to the y power. And you might say, well, wait a minute, Metzinger, that is not 1 over x. Well, look at what e to the y was could be substituted with. We said at the very beginning of the problem that e to the y is equal to x. And I put that back in, and that makes 1 over x. So let's use our derivative rule to find the derivative of the natural log of 2x plus 2. So what you could say is, if you wanted to use the U-Substitution Technique, is I could say u is equal to 2x plus 2. Rewrite my problem as y equals the natural log of u. And so if I took the derivative of both sides, so the derivative of y with respect to x is going to equal the derivative with respect to x of the natural log of u, which is going to equal 1 over u times du over dx. So I need the derivative of u. Well, the derivative of u in this case is 2. And so I put all that in. So it'd be 1 over the inside, 1 over 2x plus 2 times 2. And then we could simplify that. That would be 2 over 2x plus 2, which is the same thing as 1 over x plus 1. Now let's do it again. Find the derivative of the natural log of tangent of x. So we could let u equal the inner function of tangent of x. And so we have our equation that's f of x equals the natural log of u. I want to take the derivative of that. So f prime of x would equal 1 over u times the derivative of u with respect to x. So du over dx, the derivative of tangent is secant squared. And so I'd put all that in over here on the right-hand side. So 1 over u. So we'd have 1 over tangent times secant squared. Which, if I go through the process and try to simplify this, we can do some trig identities. That would be cosine over sine times 1 over cosine squared. I could cancel out a cosine. We'd have 1 over sine of x times cosine of x, which would be secant times cosecant. Let's extend the technique that we have for the derivatives of logarithms, and let's look at some much more complicated problems where we actually have some problems that don't even have logs, or some problems that have logs that are not natural logarithms, and how we can still find their derivatives. We can take and use the properties of logarithms, which I have shown here as a part of a review in this table, to do very complex derivatives. So let's look at this function here of f. And let's say I wanted to find the derivative of this function here. Well, what we can do is I can take this function, say y equals x times the square root of x squared plus 1 over, and I have x plus 1 to the 2/3. So I just wrote this as y equals. If I take the natural log of both sides, so I have the natural log of y is equal to the natural log of that whole side there. And I wanted to take the derivative. So if I took the derivative of this line here, I would have 1 over y times dy over dx is equal to the derivative with respect to x of that natural log function. And you might be saying, well, how in the world did this actually help me in terms of finding the derivative? Because I have to do the derivative of this crazy natural log function here. Well, before we differentiate, we're going to use the properties of logs, and we're actually going to expand this whole piece here. And what we have is we have 1 over y times dy over dx is equal to the derivative with respect to x. Now, I want to break that ln into as many pieces as I possibly can. And so we break up, we have multiplication, we have division, we have exponent powers. And so we break it up, and this will become the ln of x plus the ln of the square root of x squared minus 1 minus the ln of x plus 1 to the 3/2 power. Now, if you remember your properties of logarithms, you can take all exponents and write them as coefficients. Now, we're looking at a line that is much easier to take the derivative of each part. I can take the derivative of ln of x. I can take the derivative of the ln of x squared minus 1 pretty easily, and the same thing with the ln of x plus 1. And we're going to do that. Let me come up here to this next line. So we have 1 over y times dy over dx is equal to, and I'm going to start taking all of those individual derivatives. The derivative of ln of x is 1 over x. And then I'd have plus 1/2 times the derivative of the natural log of x squared minus 1 would be 1 over the inside times the derivative of the inside. And then now we're on to 3/2 times the ln of x plus 1. Its derivative would be 1 over the inside times the derivative of the inside, which is 1. And we start looking to clean this up a little bit. And we have 1 over y times dy over dx is equal to 1 over x plus, now I have those 2's will cancel, so I'd have plus x over x squared minus 1 minus 3 over 2x plus 2. Now we want to be dy over dx equal, so I'll multiply y to the other side. Dy over dx is equal to y times 1 over x plus x over x squared minus 1 minus 3 over 2x plus 2. Well, we can take and we can substitute y. So that way our whole derivative is in terms of the same variable. Y is that rational function there, and we'd have our final derivative, where the derivative of this would be x times the square root of x squared plus 1 over x plus 1 to the 3/2 times 1 over x plus x over x squared minus 1 minus 3 over 2x plus 2. All right, let's look at this one here. We want to take the derivative of f of x is equal to log base 5 of the square root of x. And something we can do here right out of the gate is we're going to use a property of logarithms, because the square root of x is really x to the 1/2 power. And so I'm going to pull the exponent out front. So at least I made it a little easier to differentiate the inside. So it's 1/2 times log base 5 of x. Now, we don't have a derivative rule for logarithms that are not the natural logs. So what we would have to do is we'd have to do the change of base formula. So we need to change the base. So the log base 5 of x is equal to the natural log of x divided by the natural log of 5. That's how we change the base of a logarithm. And so I'm going to substitute that in. And so we'd have 1/2 times the natural log of x over the natural log of 5. Now the natural log of 5 is just some number. So I'm going to rewrite my problem as f of x equals 1 over 2ln of 5 times the natural log of x. Now we're ready to find the derivative. So the derivative of this, f prime of x, because I have the natural log now, we know what the derivative of ln of x is. We'd have 1 over 2ln of 5 times 1 over x. And we can just leave our answer like that. Okay, now let's look at the next one. So let's use our rules of logarithms and the implicit differentiation technique to try to figure out how we would take the derivative of 3 to the x power, because we just have a derivative rule for how to take the derivative of e to the x, and this is 3 to the x power. So what we're going to do is we're going to write an equation, y equals 3 to the x. Now we've just learned or seen how to take the derivative of a logarithm that is not the ln. So what we can do is we can take the in fact, let's just take the natural log of both sides here. So we'd have the ln of y is equal to the ln of 3 to the x. Use properties of exponents here. So ln of y, or properties of logarithms, would equal x times the ln of 3. And let's take the derivative of both sides with respect to x. So the derivative with respect to x of the natural log of y equaling the derivative with respect to x of x times the ln of 3 I'd have 1 over y times dy over dx is equal to the ln of 3. Well, I just multiply y to the other side. So dy over dx is equal to the natural log of 3 times y. Now y was representing 3 to the x power. So our derivative, ln of 3 times 3 to the x. Now, we can generalize this for any exponential function where we don't have base e, and if we have some constant, call it a. Where if I'm taking the derivative of a to the x power, the derivative would be the natural log of the base times the exponential function, a to the x. Now, if I had a function of x in the exponent, call that function of xu, and I wanted to take the derivative with respect to x, according to the chain rule, it would be natural log of the base times the original exponential function times the derivative of the exponent. That's what the du over dx is, the derivative of the exponent. And so let's find the derivative of the following problems. And we kind of get all of our rules put into one here. So the derivative of f would be, in this case, so I have e to the 5x, and I'm not going to use U-substitution here. The derivative of e to the 5x is going to be e to the 5x times the derivative of 5x, which is 5. Then I have plus the derivative of 7 to the 2x power, which is going to be the natural log of 7 times the original problem, 7 to the 2x power, times the derivative of the exponent, which is 2. Then we're going to plus. We have the natural log. So the derivative of the natural log is 1 divided by the inside times the derivative of the inside. And that's almost all we can do. I'm just going to rearrange the terms a little bit better, or the multiplication. So we have 5 times e to the 5x plus 2 ln of 7 times 7 to the 2x power plus 2x over x squared plus 4. Last problem here. All right, so we want to take the derivative of e to the tangent of 3x plus 6 times x squared plus log base 2 of secant of x. Okay, well, we know that we're going to have to rewrite that logarithm. So let's go ahead and rewrite that logarithm to be an ln. So we'll do the change of base rule and rewrite our problem. So log base 2 of secant of x is going to be the ln of secant divided by the ln of 2. Now remember, the ln of 2 is just some number. And so now we're ready to take the derivative. So the derivative of e to the tangent of 3x is going to be the exponential function e to the tangent of 3x times the derivative of tangent of 3x. Well, the derivative of tangent of 3x is secant squared of 3x times the derivative of 3x, which is 3. So I had the composition of 3 functions to account for there. Now we have plus the derivative of 6 to the x squared power. All right, the way that works is it's natural log of the base, ln of 6, times the original exponential function, 6 to the x squared power, times the derivative of the exponent, which is 2x. And now we're on our last term. Well, what I'm going to do in the last term is I'm going to pull the ln of 2 off of the ln of secant. So I'm going to have 1 over the ln of 2 times. And now I'm going to do the derivative of the natural log of secant. Well, the derivative of the natural log of secant is 1 divided by the inside times the derivative of the inside. And so here's my derivative line. I could just do some cleaning up here a little bit. Can't really do but so much. So 3 times secant squared of 3x times e to the tangent of 3x power plus 2x ln of 6 times 6 to the x squared. And I don't know what all we can do for that. We can cancel out a secant. 1 over the ln of 2 times tangent. So I'd actually have tangent of x over the ln of 2.